Well, this video is going to be Chapter 6, Part 1 of 2 for the Netacad CCNA Course 1. Again, this is Chapter 6, Part 1 of 2. The second part, there will be a link at the end of this video. Should be on the right-hand side somewhere down there. My name is Jason Johnson. Thank you for watching these videos, and if you find them helpful, or if you want to follow the channel or get updates on future videos, just click the subscribe button. If you have any questions for me, you can leave a comment below, and I get those on my email, and I'll try to leave a comment back or email you back as quick as possible if you do have any questions. Okay, so let's get started with Chapter 6. We're going to do a couple of different things here in the two-part video. The first video, we're going to look at an introduction to the material. We're going to look at network layer protocols, and then we're going to look at routing and what routing is. In the second video, we're going to look at routers and what they are, and kind of as an overview. And then we're going to look at the configuration of a Cisco router, or at least the basics of a configuration of a Cisco router. So in this course, we've talked about protocols and what protocols are, so I'm not going to go back over that again. But when we look at the network layer protocols, we're talking about the layer 3. So we've moved up to the layer 3 now of the OSI model. And at the end of this section, you should be able to describe the purpose of the network layer and what it does in the data communication process, explain why IPv4 protocol suite requires other layers to provide reliability. So IPv4 can't do it by itself at layer 3. It requires other layers, and that includes media and unreliable and connectionless. And explain the role of the major header fields in the v4 packet, and explain the major header fields in the v6 packet. So network layer and communication, how does this work at the layer 3? So end-to-end transport processes, they address end devices. They do encapsulation as well at the layer 3. It does the routing at layer 3, and it also does de-encapsulation because it has to read that packet as it goes through. So if we look at this process here, the host needs to send a message to 168 or 192.168.36.5. So what it does is it packages that information, it sends it down. The encapsulation happens on the data at layer 4, and then at layer 3, the networking process, and then all of the routing information gets added, and then it sends it on through, it goes through the network, and then it gets de-encapsulated on the other end. And when we're looking at the OSI layer here, the 7-layer model, the version of the v4 and the v6 all operate at the layer 3 here, the Internet Protocol version. So let's look at the characteristics of the IP protocol. It is when we encapsulate the IP, the transport layer PDU, or the segment. We have a segment header, and then we have our data. The transport layer, and this is kind of pixelated here. This is kind of interesting on this PowerPoint slide. But the transport layer adds a header so segments can be reassembled at the destination. So it adds information so it can be repackaged back together. And what happens here is that transport layer PDU gets encapsulated in there. The IP packet sent. So the IP header gets put on there. And that's the network layer encapsulation, so it knows where it's coming from, knows where it's going to. It has all the addressing on there, so that it unpackages it on the other end. And then this information is encapsulated, and it gets unpackaged so the other end can read that information. And as we blow it up here farther, no connection with the destination is established before sending data packets. That's one characteristic of an IP packet. It's connectionless, which means essentially what that means is it doesn't need to get a response from the other end. It just shouts out, and it just says, "Hey, here I am. I'm sending packets at you. Whether you're ready for them or not, they're coming your way." It does best effort, and by best effort, it says, "I'm going to send the packets. If they go through, that's good. I'm just going to give my, it's kind of like the meh. If it goes through, it goes through. If it doesn't go through, it doesn't go through." It's the same reason, and a result of this is when you go to maybe pull a YouTube video down, or you go to Twitter, or you go to Facebook, or you go to a website, and you don't get the website, or you don't get all the information on the page, or the whole information doesn't load. That's a best effort. It kind of like gives you what it can, but it doesn't get too worried about the rest of it not going through. It just does best effort, and it's media independent, which means it doesn't depend on the media. It sends it and it goes. So you need to understand what connection and connectionless, how that works on a and you also need to understand the differences between connection and connectionless. Excuse me there. Had a little cough in my throat, had to pause. But the difference between connection and connectionless and the different protocols and which ones use the different ones, we'll get into those in later videos. But for now, you need to understand that there is a difference, and you need to understand just without having to look it up. This is just something that you need to know in the networking area. What happens with the connectionless? So you send a letter in the mail. Imagine this is if you're going to send a letter to Jane. So Bob's going to send a letter to Jane. You throw it in the mailbox. The truck delivers it, may or may not, but you don't really know if it got there or not. Or let's just say you send an email to somebody. Well, you don't necessarily know it got there. So that's what with the connectionless, you just send it and it goes, but you don't really have a receipt on that. Also, the receiver doesn't know what's coming. It just goes. And we'll talk about connection-oriented in a little bit later and how that's different. But on here, this is another representation of how it works here. If the sender doesn't know if the receiver's there, if the packet's arrived, if the receiver can't read the packet, receiver doesn't know when it's coming. It just goes and it shows up. And then over here, let's just say that this is a web server, and the web server just sits there with the web pages or the web information. It just sits there and says, okay, I'm ready for you. If somebody requests my information, that's fine. If not, I'll just sit here and wait for you. And the best effort, this is another visual on the best effort. It's just basically saying packets are routed through the network quickly. Some packets may be lost. That's a side effect of this. So 3 of the packets get sent, 2 of them got through. And then what happens on this other end, we only got 2 packets, so we dropped packets. Or we may have had a stutter in the video. So if you're watching a video on YouTube or you're listening to an audio across the internet and you get some kind of stutter in there, or you get some break in the information, or the video pauses for a few seconds, that's probably because the packets are being dropped, and so you don't get all the information on there. And it's media independent. It doesn't matter what type of media you're sending it on, whether it's a copper Ethernet, serial line, whether it's fiber optics, or whether it's wireless. It goes through all of them. It's media independent. It can go through all the different types of media. Okay, so let's take a look at a version 4 or an IPv4 packet. An IPv4 packet, from a visual standpoint, is built this way. You have your version and your internet header length. That's the first, byte 1. Byte 2 is your DS, your DSCP, your ECN. And let me just make a statement here. You need to be familiar with how this is built, but you don't really need to memorize this for the Netacad course, at least for the first course. You don't need to memorize how this is all built out, but you are going to need to be familiar with this, because you may see a question or two on how this is built, but you may not have to actually put it together this way. But you do need to know. You may not need to know that, the DSCP and what that is, or the ECN. You don't need to know exactly where the bytes are on here, but you do need to know that the IPv4 header has a time to live built in. The protocols are built in, your source IP, your destination IP, and then some of the services and total link. Again, you're not going to have to rebuild this probably from memory, but you need to be familiar with this so that when you look at it, you know where things go. So what happens is this packet, let me just clear the board here. This packet, the packet priority, the time to live, the TTL, that is basically saying how long is this packet going to hang out on the network before it dies, so that it doesn't just bounce around forever. The protocol, your source IP, your destination IP. So let's look at the V6 packet then on that. And why we have version 6. Version 4 is going away because we are running out of, or have run out of, addresses for the version 4. Internet routing table expansion. We needed a bigger set of numbers. The world has gotten to be a much bigger place than what it was in the 1970s and 1980s when they first came up with version 4. And so in the 1990s, and I believe it was 95, but I may be wrong on that. You can go Google it when version 6 came out, first come out. But it's taken a long time to get here with getting version 6 in place. But there's a lack of end-to-end connectivity, which version 6 will bring along. So IPv6 gives us more address spacing, and it improves packet handling, and it eliminates the need for network address translation. So NAT goes away. We don't really need that. So just as an example of how much bigger version 6 is from version 4. Version 4 gave us 4 billion IP addresses. 4 billion. Now, back in the day, if you go back and research the history on the networks, and I'm just going to spend a few minutes here and talk about this, or not even a few minutes, but I'll just spend about a minute or so talking about this. But back when they created the internet and they came up with IP addressing, and they said, at that time, back in the 70s and 80s, they were thinking, well, we're going to connect universities, we're going to connect military sites, we may connect some businesses into this. So we're probably talking, a few hundred, maybe a couple 100,000 IP addresses. Well, the internet changed over time, and it becomes something that was not originally intended, to where all of these devices are connected now, and we have the Internet of Things. So refrigerators are connected, and everybody's carrying just on your personal space. You probably have a phone, maybe a device, maybe a laptop, a desktop. So you may be carrying 2 or 3 devices that have IP addresses. So we have ran out of IP addressing, and we use network address translation to take care of that right now. But we have come up with the version 6 now, and we have 340 undecillion IPv6 addresses. Undecillion. That's a very large number. It's hard to imagine how big that number is. I've heard it described as that's an IP address for every grain of sand on the planet type of number. It's very large. So we're gonna have enough IP addresses for a long time to come. When we encapsulate the IPv6 packet, it looks similar to the version 4. We have the version, and then and version 4 is built inside the version 6. So when we're looking at the version 4 header here, and then we go and look at the version 6 header, I'll show you the differences here. So the version 4 to the version 6. So if you notice the difference here, our version stayed, our source and IP. But if you notice something else, they simplified the header. They simplified it. So we had all of this information here. Now they've pared it down. So there's not as much to look at when we look at when I say look at, that's not the right word to say. There's not as much to it, so it's simplified, which makes it easier to deal with. Some of the advantages of version 6, it's better routing efficiency, no requirements for processing checksums, so they got rid of checksums, simplified and more efficient extension header mechanisms, and a flow label field for per flow processing, with no need to open the transport inner packet to identify the various traffic flows, which this right here allows for better routing efficiency. So this is the explanation of why we have better routing efficiency on there. So when we're looking at that, this is the V6 packet header, and it's simplified compared to what it was with the version 4. So there's less routing overhead, obviously, is what I've already said, but you can just see the difference here. So when we talk about IPv6 and IPv4, and we talk about routing and what routing is, let's take a look at why we have routing, or what we do with routing, and why that's why you're taking this class, is so we can learn about routing. It's so that we can send information and know where it's going, or know that it will get to the right destination. So how a host routes. So when we send some information, and let's just say that a local host or a remote host, the forwarding decision, it's going to say, this PC1 here, it's going to say, I need to find some information. So it sends information out, and it says, okay, this is was my information here, because it's going to go through the switch and see if it finds it, or it's going to go through the routing process and find it on the remote host. It's looking for information. And if it can't find it locally, it looks for the remote default gateway, or remote gateway, or default gateway. But we're gonna use the term default gateway in the Netacad course. So the default gateway is your way out to find the information somewhere else. So the IP address of the R1 interface is the default gateway, and so this is a connection here. These two can see each other on the local area network here, so they can communicate through the switch. But if we need information and we're going out, let's say, to a web server, we would then go through the default gateway. Usually it's going to be a .1 on the network, but that's not always true. But that's kind of the standard, or it's not a standard, but let me just say that happens a lot of times. So if you've got an IP address that you're looking at. Usually, in most cases, it's .1, but some networks do a different number. And it doesn't matter because you can always find that default gateway. You just do an IP config and you're going to find your default gateway. So it doesn't, some people try to hide it and change the number, but it's not hidden. It's always there on the network. So if you do a netstat space -R, and I believe this is on a Windows machine. Yeah, Windows machine there. You're going to get your information back here, your IPv4 route table. And netstat is a command that you need to be familiar with and how to run and the different options. So that is something that you need to be familiar with in this course. Okay, so let's look at routing tables and how this works. So we know that we have to request information through the default gateway, but how does that really work, and how is it efficient? So the packet forwarding decision, the routers make a decision, or that information needs to be decided how it's going to route best. So the R1, or our default gateway, has 3 directly connected networks. It has a network here, a subnet here, a subnet here, and we'll get into subnetting later and how you can tell that these are different subnets based on the CIDR notation, the /24 here, and where the we're in the 3rd subnet there. We'll learn about that in future classes. But the R1 has 3 direct connected networks. See if I can say that again. Direct connected networks. We have a network here, we have a network here, and we have a network here. Let me draw that again. There, and there. And that's its route. So it knows that it can route information that way. And if we do a show IP route, it's going to show you the IP route on there. So you can get your route table. And so it builds this table and it says, how do I route this information? What are the networks that are connected to me, and how do I send this information out? So a directly connected routing table entry, and these tables get built. They're files that get built inside the operating system. And this information, you have your route source, whether it's direct connected, destination network information, and the outgoing interface. So we're going to be able to see the routing source, where is my destination information, and then where is it going out on. So this was saying it's going out on the G00, or Gigabit Ethernet 00, but G00, and then that's the IP address, and that's the subnet information right there that it's connected to. A remote network routing table entry. This is remote, so this is showing where we're connected on the other side, but it identifies the network that was learned by the router. So the routers are constantly communicating with each other, and they're sending ARP table information, and then they're sending a routing table information, and they're saying, hey, I'm a router, and what information is connected to me? Who's connected to me, and what information can you give me? And so it may send a signal out, and it says, okay, are you connected to me? And this router says, hey, I'm over here. Yes, I'm a routing table too, and here's my information. So this R1 then builds a table of information, and it says, okay, I know I've got R2 connected to me, and here's what information I know about it. And I've got G00 here and G00 here, and I've got these 2 networks, so that when PC1 requests information, this router says, okay, where am I supposed to send this? If the destination is not on this network, it doesn't forward it through. But if the destination is somewhere over here, but maybe it don't even know where the destination is. This router doesn't need to know the destination. It just needs to know that it's not here, but it may be here. It may be here. So it sends that packet over here to this router, and this router picks it up and says, okay, well, I've got it, and hey, by the way, that's on my network, so I'm going to forward that packet on, and I'm going to forward that information on. If this router doesn't see it, if this router doesn't see the final destination, it forwards it to its routers, or it just drops the packets. But if it sees another router over here, let's just say, for example, there's another router here, it would then forward it to this router, and then this router would pick it up and then try to find where it goes. And if it doesn't find where it goes, then it just drops it. One of the things that you learn in networking is about a next hop address and where the next hop is. And then we're not talking about bunny rabbits hopping, but the same concept. We're talking about route hops. And so when you do a show IP route, you're going to see your hops on, it's bouncing is basically what it's doing. And so when you, let's say PC2 requests information and it sends it through the switch and it goes to this router, here's the first hop is my default gateway. And then the next hop is here. And then the next hop is then on here because it's hopping. And so then if you go out to the internet, you're going to see multiple routers. And if you do this connected to a web page, you're going to see these hops on there. It's going to hop here to this router, then here, then here, then here until you get to your final destination. But that's the term next hop address and what that means. Okay, well, we have looked at the first part of Chapter 6. We covered in this portion of the Part 1 video, we've covered an introduction, the network layer protocols and what those what the basics are on those, and then the basics of routing and why we route. In Part 2, we're going to take a look at routers, the basics of configuring a Cisco router, and then we'll do a summary of this chapter as well. Okay. So if this video was helpful, you can click subscribe down on my channel to see future videos. And if you have any questions, you can leave a comment below. And again, my name is Jason Johnson, and thank you very much for watching my videos.